Alright, so we are doing Unit 2. It's like day 2, 3-ish. Okay? And real quick, I want to show you something from the calendar. So, day 2 on the calendar and day 3-ish, we'll go to day 2. It says we're going to be estimating derivatives of a function at a point. And number 3, day 3 shows that it's the power rule. So the reason why it's the best day in Calc, in my opinion, is the fact that forevermore you're going to learn the shortcuts, okay? And the shortcuts are very convenient, but trust me, there's a lot of algebra still coming your way. Okay, so the shortcuts are short-lived. They're fun to see whenever you're first looking at them, but then you'll realize that there's a lot that you're still memorizing with these shortcuts, okay? Today is a huge conceptual day. A huge conceptual day for sure, as far as what are you deriving, why are you deriving it, and what are you solving for input or output values, okay? So here we go. In that same post, let's go to Google Classroom. I want you to open up that the notes PDF that I gave you. And we're going to go to where it says power rule. All right. So derivative rules, guys, it's basically the shortcut here is n times x to the power of n minus 1. Okay, so for instance, let's look at A. A has x cubed. So that means it will be 3 times x to the n minus 1, otherwise 3 minus 1, so that it becomes 3x squared. This is the derivative shortcut just to get to the derivative function like that. Okay? Real quick, I'm not going to show all the work, but the setup would be the definition of the derivative. Okay? Your next test won't necessarily be, man, we got to do this long way just to find a derivative for all these functions. It's not. But there may be one or two that will ask you, showing all the work and doing it the long way, show me how to get the derivative from the definition of the derivative. Or show me how to get the derivative from all that work of the alternative form of the definition. Okay? So, definition of the derivative would look something like this. X plus h cubed minus x cubed all over h as h is approaching 0. This is equal to f prime of x. Okay? So this derivative, the shortcuts are what we begin to learn today, so that we don't have to do all of this work. Okay? The alternative form would be, in this case, f of x minus f of c, x minus c as x is approaching c. But I would not be able to do that with this one. Nice, and I see the heads nodding, and you know you wouldn't be able to do it unless I was asking you for a specific c value, like f prime at 3, or f prime at negative 5. Okay? Alright, so now, let's move forward with our rule that we just learned, and this is a big thing that I want you to make sure that you are cognizant of. We cannot leave negative powers. And the biggest reason why is the algebra manipulation experience that you're going to get. So let me give you a caveat, and those of you hearing this video or watching this video right now, the more experience that you get with these functions, the faster you're going to be able to get to the level of, Mr. Gomez, how did you know to do that? How did you know to try this? And it comes from either one of two things. Hundreds of problems, or few problems that you dissect so big time, and you're understanding why you're doing, when you're doing, you know what I mean, as far as the manipulations that I'm talking about. What are manipulations that we did in limits that sound in your mind? And I'm talking about multiplying by forms of 1. What was it that stood in your mind right now from limits? The radical, yeah? Whenever you're square rooting a square, remember that? What's another thing that was like kind of big that stood out in your mind of, it's a lot of manipulation. There's one more. the conjugate. Remember those forms of 1? Okay? So there's a lot of multiplication forms of 1 that need to stay in your brain. And what you're going to be doing during this unit is you're going to do a lot of algebra manipulation. Again, my caveat is please, please, please do your homework. Do not blow your homework off. Okay? You need the practice. Just like if you're not practicing your trumpet or if you're not practicing swimming, I promise you, you will get very frustrated very quickly. Alright, so let's go ahead and begin. It's all about, in my opinion, to make things easy for you to see, it's all about the rewrite. It's how do you see something will determine how easy it is to work through it and derive. Okay? So for instance, some people look at this and they see the square root of x, obviously, but then some people look at the rewrite of this and one might be easier than the other for them, depending on their level of experience that they're bringing to the table. Okay? Because this is power rule, I would say that this is the suggested form because the rule says bring the power down, multiply by the base, and you're going to do it to the power of n minus 1. So n is 1/2, minus 1 would be minus 2 over 2. Notice how immediately I gravitated toward the common denominator, whoops, because I'm working with fractions. Okay? So we get y prime is equal to 1/2 x to the negative 1/2. Because of algebraic manipulation, I will not accept this answer on a test or a quiz because I want you to get comfortable with knowing which pieces move when and where with negative powers. So this would actually move down to join that 2 where it looks like this. So this is a huge negative exponents, remember, skill that we learned from Algebra 2.
And does it matter whether the x is to the 1/2 or square rooted?
So there was the question right there. This right here would also be equivalent. Now here's what I'll say. I know the instructions say or complex fractions. Guys, right now I have a complex fraction, which means you have to rationalize the denominator. I'm not going to hold you to that. Not this year. Okay? You can leave a square root in the denominator. You can leave a power of 1/2. Just make sure that there are no negative powers in your answers. You with me? So don't write it out like this one. Any one of these would be totally acceptable and full credit. And you'll see why as we go through and we develop more and more. Okay? Alright, here we go. So, on part C, any suggestions? What could I do to apply the power rule to this example? Yep.
You could equal it to t to the power of -4.
It's all about the rewrite, guys. So I'm going to, and notice this, you have to understand, have I derived yet? Or am I just rewriting the position function? Okay? So what Omar just said just now, yes, we're going to change this to be t to the -4. And here's what I'll say right now. This is a very helpful thing, but knowing when and where to use it will help you or hurt you. Okay, here we go. Put this in your notes somewhere. You should only move a power up to the numerator if the top is one term and it's a constant. If it's not one term, let's say there were 5 terms up there, I wouldn't move it. It's going to be more difficult that way. If it's not a constant, let's say you had x squared or t squared up in the numerator, t squared minus 4t plus 5 or whatever, I wouldn't move it. Only if there's one term in the numerator and it's a constant, like a number, 20, -5. Okay? So now, if I use the power rule on this, it will give me, anyone? -4.
Over t to the 5th.
Okay, so t to the -5. Some of you simplified and you went straight to the answer that's acceptable, but this would be the answer so far. And yes, we need to make sure that we understand that the t would go downstairs alone, and this right here would be g prime of t. Bless you. That is a common mistake. From here, you're going to make a lot of mistakes, and I need you to grow from them. But if you don't experience enough mistakes, I'm not even kidding. If you don't, I know this sounds kind of backwards. If you don't experience enough mistakes, I think your chances of getting 100 or 105 on a test are reduced. Okay? So you want to experience these mistakes. So -4 minus 1 is the same as adding the negative. Okay? That is common. The number one mistake that you will have in this unit are negatives. Okay, here we go. So D is asking for the derivative of 5. Okay? Anyone, what do you think the derivative of 5 is? Just say it out loud. 0, right? Okay. Why is it 0?
Because it doesn't have
Because it doesn't have
an x.
an x. What other question or answers are there?
Because it's x.
It's a constant. So here we go. It doesn't have an x. It's a constant.
Horizontal lines.
Horizontal line, if you were to graph it,
It doesn't have a slope.
it doesn't have a slope.
So the derivative would be like a cusp, which we can't have, right?
So the derivative is a cusp. Now
Or
listen.
like a point.
No worries. Let's put all those 5, whatever, together. My thing that I like that was said the most out of everything was the fact that f of x is 5. And if I were to go back to the original function of what does y equals 5 look like, it would be 1, 2, 3, 4, 5. You with me? What's the slope of that line? 0. Always, sometimes? Always. So the derivative of a constant will always be 0. Does that make sense? Does that make sense? Okay. Now, someone said it doesn't have an x. I like that one too. Because technically what this is, it's 5 times x to the power of 0. Look at that. There's rewrite, what's it called? Manipulation. And I tell you these for reasons, because it's going to help you with other problems that are coming your way. It's not just, nah, I'm not going to use that one. No. Think about it, okay? If I use power rule, and I multiply this 5 with 0, automatically what do I have? 0x to the power of what? -1. And if I were to manipulate this, I have it at 0 over x to the positive 1. And we know the answer is 0. Cool? Alright. Here we go. So the derivative function can be shown like this. F prime of x, the derivative in respect to x, or it can be shown as y prime. You with me? Okay. So now what this is saying is take the derivative of this function right here, whoops, and you're going to give it respect to x. So anyone, what would the answer be here? 15x squared. Now listen, this is very important. You're going to learn it later to come, but I'll tell you right now and mention it right now. This means it's in respect to x. So if I want to give it respect, I'm acknowledging my variable as x. So let's say that I was taking the derivative of t squared in respect to x. Can someone tell me what they think that answer would be? T squared. And it's a little bit more than that. But for now, it would stay t squared. You can't derive it per se. This would have to be what letter? T. That means you give, basically you're giving t the respect that it deserves. And now when you derive it, what would t squared end up becoming? 2t. 2t. Perfect. Okay? Alright, here we go. So let's move on to some more rules, because more rules, this entire unit is rules of differentiation. And all these shortcuts are going to come your way. Okay? Derivative of a constant. You said it. The derivative of any constant is 0. It will always be 0. Okay? Because of that, This constant multiple rule, even though it's not called the power rule, I think it's the most powerful one that you will use all year. Okay? So, even though it's not called a power rule, I think it's very powerful because it makes things so much easier to look at. And you'll know what I'm talking about whenever all these integrals and derivatives have all these numbers and variables all mixed in. So here we go. It's a constant times a function. Okay? Okay. So looking at that, if you're multiplying with a constant, what you can do is you can bring it out. So imagine I just pulled this C, it could be 2, 38, whatever it is, it's a number, and I moved it all the way next to the door, way over here. And all I'm going to do now is derive x to the power of n. Go with me? And x to the power of n would be n times x to the n minus 1. And guess what we're going to do at the very end with that c? We're going to multiply it back in. So it's almost like it's not part of that derivative process. Just the things that are with the variable are part of the derivative process, and then you multiply that constant back in. Cool? All right. Sums and differences are different. If you have these, they're similar to limit laws. In the respect of, let me show you, oops. Here we go. The sum of the derivative will equal, the derivative of the sum, my mistake, I'm sorry. So the derivative of the sum is the same as the sum of the derivatives. So we're going to put right here an addition sign. And yes, it almost feels like we're distributing this derivative symbol, but we're not. We're applying it just like we did with limits back in the limits unit. And we're going to derive whatever f of x is and whatever g of x is, so that our answer will be f prime of x plus g prime of x. And then this one over here, it will end up becoming f prime of x minus g prime of x. Basically, it feels like you're distributing again, but you're not. You're applying. So you're taking the derivative of two different functions. So the derivative of f, the derivative of g, and then just subtract them. F prime of x minus g prime of x. Okay? All right. So now let's start putting just these small bits of new rules together and solve derivatives of these functions. Okay? So I have f of x is equal to 4x cubed minus 5x squared plus 7x plus 3. Any suggestions, guys? What would I have? 12x squared minus 10x plus what?
7.
Plus 7. So sometimes people get 7x confused, and they might put like just 7x or zero it out. A good way to help you with this, just off to the side, quick little scratch notes. Again, these are experiences that will help you. This is y equals 7x. Guys, you tell me, what will the slope be always on this line? 7. So that's the derivative. You with me? Okay. Can y'all tell me real quick, let's see speed-wise, what's the derivative of that?
9x squared.
9x squared. What's the derivative of that?
3e squared.
3e squared. Okay, the power rule, listen. The power rule only works on power functions. And a power function is when the variable is in the base and quantitative numbers are in the power. That's why they're called power functions.
0.
But this is not a power function because e is not a variable.
So it's just
It's a constant. It's 2.71828, 1828, and other numbers, right? And the derivative of any constant is what?
the constant.
Zero.
Never mind.
Zero.
Wait, is it not like the same thing as the d over dx, like say t squared?
So if I said, what's the derivative of 5, what would y'all say?
Zero.
0. What's the derivative of this constant? What would you say? 0. What's the derivative? You see what I'm doing? What's the derivative of e squared? It's still 0. Yes?
Does the 3 on that first one just go away because there's no x?
On this one right here?
Yeah, no, the 3
plus
at the end, it's just 0.
Oh, right here? So yeah, there's your constant. And the derivative of constant becomes 0. It just goes away. Okay? Alright, so here we go. Guys, the deeper questions, even for the small things that you think maybe are not important, you do need to ask because they are going to help you. Or the other alternative is doing hundreds of problems. Okay, and I know you don't want to have that much homework. So here we go. Our second example. Let's put the skills together that we just learned. But let's also put years of algebra practice into use of how we can make it simple. Okay? So with what I have here, what do you suggest that I do algebraically manipulate? Omar.
Divide all terms by x.
Okay, he says divide all terms by x. Any other suggestions?
Bring the x up to x to the negative 1.
Bring the x up as x to the negative 1.
Well, it's not one term. It's not constant.
That's good thinking. Let's think some more. It's okay. We're going to learn from all this good and bad. I need you to learn it from good and bad. Don't be afraid to make a mistake. I promise. The higher grades will come from those mistakes. The earlier they're made.
I guess like once you like divide every single term by x, like you can for 4 over x, you can bring the x since it's just one term.
Man. Okay, here we go. Let's put all of these things together now. Omar led us off perfectly as we should look at this. And Brady even said it as well. We don't want to bring the x up because the top doesn't have one term. How many terms does it have? It has 3. Because terms are separated by addition and subtraction. Okay? But also we don't want to bring it up because the top needs to be, if it's one term, it needs to be what? A constant. No variables in the top. So let's leave it at the bottom and we're going to do what Omar said. Here we go. 1/2 plus 3/2, 5th grade example, we know is 3 plus 1 over 2. We've become very comfortable going this direction. And calculus does a lot of things algebraically, manipulation-wise. This. So Omar is exactly right as far as how we should look at this. We need to, divide all of these pieces, and this almost feels like an infinite limit, but that's not what's going on right here. And you tell me, what's the mistake that I've made? Knowing every single detail is a big piece of this, because one little thing can throw the whole thing off, and I'm not even kidding. That's this kind of unit.
You said y prime?
Because I put y prime. You have to know, where am I at? Have I derived yet? Or have I rewritten? Okay? Please make sure you understand the difference. So now, I'm going to reduce and always simplify my life before I start deriving. And I have 5x to the 4th. I have 3x to the 3rd. And just like Robic said, this one I'm going to move. And the reason why I'm going to move it is because, what, Christian? Why did I move the x up in this case?
Because it's only one constant.
Because it's one term and it's a constant. Okay? So now, let's do the power rule. Okay? So, Taylor, what would be the power rule of this first piece here? 20x what? Yep, 20x cubed. All right, Matthew, what's the next one?
Negative 9x squared.
Perfect, negative 9x squared. Jordy, what's the last one? okay? Minus 4x to the power of negative 2. And Jordy, can you tell me why I drew this way over here on the right side? As scratch work? Because I'm going to have to change that negative power. So my final answer will be minus 4 over x squared. That would be the derivative. How's that?
Oh, you drew. Okay.
Any questions? Yes?
Can you rewrite a derivative, like instead of doing the side, just add it as the same step?
Yeah, you can do that. I just wanted to, just so I'm running out of room.
Right.
Okay? Alright, so here we go. Let's move on to putting graphing with the algebra. Okay, here we go. I'm at 1, 1. Okay, we're estimating the slope of the tangent line to this function at 1, 1. And then we're going to verify it analytically with calculus. I wrote a lot, I circled a lot, I highlighted a lot. To me, for what I'm trying to show you in this unit for sure, there's one word that I highlighted up there that's very, very, very important. What do you think it is? Estimate, slope. What other, at? I'll give you one more. Okay, so the most important word is at. Okay? Because at will tell you so much information on different levels. At here means position. At here means how fast something is moving velocity-wise. At here will tell you how fast something is accelerating. You with me? So at, here comes that inception analogy, will tell you at a certain point of time, there's 3 different realities that we're trying to analyze. Okay? Here we go. So, here's my graph. My graph of x to the power of 2/3 is right here. And what we're trying to do is we're trying to find the slope of this tangent line. And if you were to just guess from what you see, Braden, what would you guess that slope to be? What would you say this line's slope would be? Guess it. Again, good or bad, I want to hear what's in your head. Okay?
Less than 1.
Less than 1. He's saying the slope is less than 1. Okay? What other guesses are out there?
2/2.
1/2. Okay? I heard 2/3. Approximately 1/2. I heard 2/3. I heard less than 1. What other ones are out there? Nate? And if you agree with one of these, you can second it.
I second 2/3, I guess.
Okay, 2/3. So far, 2 people have said 2/3. Okay, let's check it out analytically and do the calculus. My slope of this function will come from what is the derivative equal to. Okay, here we go. So y prime, which is f prime of x, they mean the same thing. Guys, just like way back when in Algebra 1, we know that this was true. Well, then this is the same as that, which is the same as that.
I thought you said acceleration was f double prime.
It is double prime. So over here, there's double.
But you said that that line was trying to find acceleration.
Velocity.
Wait, what?
I thought you said that that line you said was trying to find acceleration.
No. This is not trying to find the acceleration. This is acceleration. This is velocity. This is position. Okay, so listen. This is a good mistake that's being made right now. The blue function is this. You with me? And the derivative is here. But we need to find what the derivative function is. And that's what we're about to find out by differentiating x to the power of 2/3. So let's use power rule. And what does that become? 2/3 times x to the power of
-1/3.
-1/3. which is the same as 2 over 3x to the power of 1/3. Now this is big. It was a good mistake to make, and the timing was awesome. It always is. 2 over 3x to the 1/3 is the derivative function, but it's not the slope. You know what people do whenever they mess up on the test? They think that the 2/3 is the slope because they're looking at it like this. They're looking at this like y equals mx plus b. And they feel that this m is the same as this 2/3 coefficient. But it's not. That's a big common mistake to make. This m right here, the slope of this red line, is actually the answer that you get here. You with me? At a certain x value. That's why it's all about those two letters. So over here, when x is 1, notice that I didn't put the y value. I'm only looking at that point's x value. You with me? That's my point in time. There's that analogy of inception again. That x that I just shaded or gray will tell me what it will be. So let's go ahead and plug it in. What's my slope? 2/3. And it's just coincidental that it worked out to 2/3. Okay, so what I would want you to get comfortable with is to write f prime at 1 is equal to 2/3. So the slope at x is equal to 1 equaled the output of 2/3. Okay, just for the first couple, I want to make sure that I explain as much as mistakes that I can, and at the same time let you drill in the conceptual understanding.
So if we had to solve, like algebraically solve for it, we'd use the alternate method and plug in 1 as c.
Okay, so to me, I don't think you should really ever I don't think you should ever use alternative form unless you're asked to do it. Know how to do it. But I think you should always try the definition of the derivative. Are you with me? Because once you get the definition of the derivative and you want to find it at 1/1, you just plug in that value. What if you wanted to find it at 2/1? You plug in a 2. At 30/1, you would plug in a 30. That's your at value. Yes, dear.
Is the point they give you the point where it touches the...
Yes, that, okay, oh, this is a good time to see what each level means, okay? So if I put this x value of 1 right here, it spits out a y value of 1. You with me? So that point that it just created would be where it's located. You with me? And then if I put it into the derivative function, we saw that it gave us 2/3. At that same point, it's the slope of that. And I'll stop for there for now, because there's a lot more to that, but that's like in a couple of units. Okay? Awesome questions, guys. Awesome, awesome questions. All right, so let's move on to this one. The equation of the tangent line is AKA the point-slope formula. So way back when in Algebra 2, we learned this equation, and we learned this equation. And I'm willing to bet that almost all of you preferred this equation, and you're like, ugh, to the point-slope. Here's what I'll say. Calculus is kind of backwards, okay? We're going to prefer this equation, and you will see and understand soon why we prefer that equation, okay? The speed that you will use this equation with, and the further context that it connects with different concepts later in the future, this is the better form. Okay? Here we go. And if you don't know why, let me show you right now, because I think someone's contemplating it right now.
I'm sort of just connecting something in my head.
What did you...
It's the importance of the at gets into the point slope form too.
So this supports the at for sure. The at is supported in the point slope form immediately. Okay?
I
Yes.
was thinking it's actually the definition of the slope. You just multiply.
Oh my gosh, this is amazing. That's why you guys are you're strong. You're a very strong class because you see a lot of things before all this practice of homework. This is awesome. So this is a manipulation of y2 minus y1 over x2 minus x1, which is the derivative per se. So you've been doing calculus without even knowing it since Algebra 1. Okay? So here we go. Let's keep going. You're like, ooh, what? Anyway, so here we go. So we're looking for the equation of the tangent line at, this is an important word. Let me underline it. Okay? And we're going to look at 1, 7. Okay? So 1 is your x value, whoops, which is way over here. And then 7 is your positional y value. And now we just have to come up with a slope of this function right here at what? At 1. We're trying to find the slope of this. So the slope at x equals 1 is now in calculus f prime of 1. You with me? So here we go. Let's change this so that you understand what I'm doing to f of x equals 3x squared plus 5x minus 1. What's the derivative? What's the derivative? What's the derivative function of f prime of x? 6x plus 5. Now listen, here we go. I'm wanting to know the slope at 1. Think about what I've said today. Someone who doesn't know the answer will make this mistake. They will say f prime at 1 is 6. What mistake did they just make? They think that this is y equals m, and then there's my slope. My slope is 6. But again, what two-letter word is important for them to not make that mistake? Is at. Because we need to plug in 1. Okay, we need to plug in this 1 into this function. And it will be f prime of 1 is equal to anyone. 11. So 11 is the slope that we're looking for, that we're going to plug in way over here. Okay? So the equation becomes y minus 7 is equal to 11 times x minus 1. And this is good enough for me. Simplify at your own risk. You don't have to simplify this. Some people will look at this and they'll be like, I don't like the way that looks. I'm going to move this over and get a negative 4. And this will be my answer. Either one's fine.
Wait, how'd you get that again?
I just distributed the negative, or sorry, the 11.
No, from point slope. Like, how did you get from f prime of 1 to using the point slope for?
Oh, so I found 11 as my slope, and I plugged it in here for m.
Oh, and then use the points.
Yep. And that, hence, and I know I used to do this a lot too. Oh, that's why they call it the point slope formula. Because you're using a point and a slope. But I'm one of those that doesn't like to read directions. And if you have a lot of those epiphanies, probably you're one of those people too that don't like to read directions. Okay? Alright. But they're good epiphanies still to have. Just make sure we have them. Let's go to the derivative of two trigonometric functions. Okay? And then we'll do some real conceptual problems because we're going to do those for bonus points. Alright. The derivative of sine, I'm wanting to hear your ideas. How could I find the derivative function for sine? What could I do? Because you guys have some really good ideas. And the fact that you know a lot of stuff before I even finish trying to teach it, we're not trying. Teaching it, I just want to see what you're thinking right now. What do I do? Robert?
You could use like the definition of a derivative.
Okay, you could use the definition of the derivative. If you did that. you would have sine of x plus h minus sine of x, which is f of x. And it could be over h as h is approaching 0. You could. Remember that? So it's been a while. But does anyone know the identity? And this is amazing that you referred to this. Does anyone know the identity? And I'll be very impressed if you, without looking at notes, do you remember what this is from memorization? What was it? It's not negative cosine. What is the identity of sine of a plus b?
Is it just cosine?
No. So sine of a plus b, remember in trig? It was like sine of a cosine of b. Y'all remember this?
No.
Oh, minus sine of b cosine of a. Do you all remember that? Okay. Oh, it's been a while. It's been a while since we've done this identity. So this right here would look like sine of x cosine of h, because that's what you're doing as far as the x plus h, minus sine of what? H cosine of x. You're still subtracting sine of x. It's still all over h, and it's still approaching 0. Do you see what's going on? Now, what you could do here, algebraically, to like make things work out, and I'm going to let this marinate for a little bit. I'm going to go to another way that I can show you, but then we'll put them together and we'll see what the sine's derivative is. Okay? Here we go. I'm going to graph the sine of x function. Okay? Can someone tell me what this value is right here? A negative what? No.
Negative pi over 4.
Negative pi.
It's just
Okay, so this is negative pi. Can someone tell me what this one is?
pi over
Oh,
2.
why did I put pi over 2? This is negative pi over 2, and this first one was negative pi. And then we're going to put these two together. Okay? So negative pi. What is this x value? Pi over 2 and pi. And of course this is 0. Okay? Now, there are two derivatives that I can find just like that from what we learned last time in class. Graphing functions derivatives. Alright? What are the two derivatives that you know for sure? The derivative at negative pi over 2. What is it?
0.
It's 0. Horizontal tangent. Nice. And then the derivative at pi over 2. So look, what I'm about to do is I'm going to graph, on top of this, I'm going to graph the locations of the derivative values. So at negative pi over 2, the slope is 0. At positive pi over 2, the slope is 0. What is the derivative at 0? 1. So at 0, I'm going to put 1. Do you see where I'm going with this? Let me draw one more period of sine. One more period of sine. And not at 0, but at pi. What do you think the derivative would be at pi?
Negative 1.
Negative 1. So get this. Oops, I did that a little bit too early. It's like this, this, and that. The derivative of the sine graph is what?
Cosine.
Cosine.
I have a question.
Yeah.
Why is the derivative of 0 1?
No, the derivative. Oh, listen to this. Did you hear what he said? He said, why is the derivative of 0 1? No, the derivative of 0 is 0. But that's not what I said. I didn't say, what is the derivative of 0? I said, what is the derivative at 0?
Oh, is it 1?
Yeah. At 0, the slope would be 1. It has a tangent slope. A two-letter word can fix your understanding for sure, okay? But it could also throw it off. So thank you. Thank you for that, because we're going back to the importance of that two-letter word.
Do
Okay.
we just know it's one, or?
Okay, so, and I see what you're saying. Like, how do you just know that it's one? This right here is looking at the unit circle per se. Go with me? So if you're looking at the slope of sine of x, like a unit circle, and we went to 0, we can look at, oh, I see what you're saying now. First of all, let me ask you this. Do you agree that the graph's derivative, which is blue, is similar to a cosine graph? Do you agree that?
Yeah.
Okay. So with that being said, when I'm looking at this over here, you can use your y and x values to see what would the slope be there. You know what I mean? As far as like plugging in those values into the, like cosine of x. You with me? If cosine of x, which is this graph, is the derivative function, well then at 0, what's the cosine of 0? It would be 1. So that's where that 1 came from, per se.
Okay.
So it's unit circles where
So
this 1
since-
comes from.
Since cosine is the derivative of sine, we use cosine's value.
Yeah, cosine of 0 would be 1.
Gotcha. Okay.
Go with me?
Yeah.
Now, I know that there's a lot going on there. Let's go back over here to this one. Because I know you love algebra. And I learned that very soon, that very easily and early, that you love the algebra proof more than a graph to show me what it should be. Okay? So look at this. What do you see that you could take out, basically, from the numerator? Do you see anything that you can take out GCF-wise? Sine of x. You with me? Watch this. I can take out sine of x from cosine of h minus 1. Do you see what I just did? I am looking at these two terms, and I GCF'd out a sine of x. Okay? It's all over h, right? Do you agree? Okay. So this would be over h. But I still have this other piece that I have not contended with. Sine of h, cosine of x, all over h. You with me? So what I did was, first of all, I grouped those two green circled pieces to form this. And then I have this left over, and because it's all over the same fraction, I broke it up into two fractions. Are we good? All right. Let's see how soon we forget. Hopefully not too soon. What will this, with h approaching 0, equal? It will equal 0. Remember we did that from way back when? What will this, with h approaching 0, equal? 1. Remember those two that we memorized? So it's 0, and then you have this cosine over here. And I think the way, there's a negative here that I messed up the order on. But this becomes a positive cosine of x is what it becomes. Okay? So listen, let me fix this real quick so that you're not confused of what just happened. Did this equal 0 last time, or was it like 1 minus cosine over h? It was the 1 minus cosine over h. Are you with me? So now here we go. This is what we're going to do. Just so that you can understand, at the very top, I can take out a negative from everything. I want you to see the algebra, and I want you to feel comfortable. And no, you're not going to have to do this with all the trigonometric ones. I'm just showing you for this first one, because where Rovik was going with it. Okay? If I took a negative out of this top, it could look like this. A negative, oops. it would be a negative sine of x cosine of h, a positive sine of h cosine of x, and a positive sine of x could look like, oops, GCF'd out with the negative. Okay? Do you agree that if I redistributed all that out, I would get the same thing over here? Okay, so from here is where we would GCF out those pieces. Now watch, where you would have 1 minus cosine of h. Okay, so this would actually change to the 1 minus cosine of h all over h. So it would look like this. 1 minus cosine of h. The sine of x is here, and it's all over h. You with me? Okay, I don't want to lose you, and I think I'm losing you for now. No worries. I think I'm gonna stop there with this, but it does equal for sure a cosine of x. Okay. All right. Let's come back, and if I need to re-record that, I will, just for clarification. So the derivative of cosine of x is negative sine of x. Okay, so here are the first two that we're memorizing. First two of a lot that we're memorizing. Okay, so what is the derivative now of this function?
12x
12x.
plus or minus 5.
Oh, so it's minus. So 12x minus 5
Sin x.
sine x. Okay, what you could have done is you could have put this 5 constant multiple rule, just put it off to the side, move it out of the way. And the derivative of cosine we know is negative sine. And then multiply that 5 back in, and that's how you get negative 5 sine of x. Yes?
Why is cosine positive but sine is negative?
Why is cosine positive and sine is negative? Let me record that video separately, and then I'll show you. Okay? Because I just felt like some people were getting it, some people weren't, and I just didn't want to keep going with it at the time. I want to go still to the conceptual application of what we're doing with these derivatives. Okay, here we go. So what I'm going to do is, you tell me, determine the points, there's that important word again, at which the given function has a horizontal tangent line. Suggestions. What do I do? Yeah, go ahead.
You get the derivative of f of x, and then
Okay, so here we go. Let's find the derivative, and I'm going to follow him. What is it?
so it's 3x squared minus 12.
Okay, and why did you get the derivative?
So we know it's a horizontal tangent line, so the derivative is going to be 0.
There you go. Horizontal tangent line slope. Now you're in calculus notation, 0. So we go back to algebra 2, and we're going to set our derivative function equal to 0. Now my suggestion to you is mathematically right here, so that you can make this easier for you. What do you think I would suggest for you to do? How do we find it? Let's find it. We're trying to find the points at. So we're trying to find where do these x's occur when the slope is 0. There we go. So the 3-letter word here, and I know it seems so simple, but I promise this is where a lot of people will do something else, is GCF. So we have 3x squared minus 4. There's your difference of squares. Right? So x squared minus 4 will become what factors? X plus 2x minus 2. So now, this is why we did these skills so much in Algebra 2, because we're using them for these real-world application, or conceptual understanding and application. What are my values here, guys? What will they be?
2 and
Yep, negative 2 and 2. Are these my answers? They're not my answers. They tell me where they're at, but they do not tell me the points. Okay, so the points. That means I'm going to take this -2 and I'm going to plug them into the position function so that I can see what is that point going to be. And then I'll plug in this other 2 so that I can see what would that point end up becoming. Okay, so -2 cubed, -8 plus 24, what is that? 16. And now put +2, so 8 minus 24, -16. You all agree? All right. Are we good? And if you were to graph out x cubed minus 12x, and you were to see on the graph if those horizontal tangents did in fact occur at those points, you could quickly check that for a graph, and just so that you can conceptually see it, I'm going to do that just real quick.
So,
Yep.
are those like the local minimums and
Nice, and you are 2 units ahead. Yeah. So local mins and local maximums and how we relate all this is definitely where we're going on this. So let's go to Control Add a Page. We're going to add a graphing calculator page. And we're going to graph our original function that we had, x cubed minus 12x. Here we go. X cubed minus 12x, and you get this graph right here. And yes, if I zoomed out, I would be able to see the local mins and maxes occurring at those 2 points. So we could say menu, zoom, out, and then yes, we could say the center is here, and we can just keep zooming out. And just like Alex said, at -2, it would be at 16. And at 2, it would be at -16. Because that's where the horizontal tangents are occurring as far as showing us these horizontal slopes, of 0 and 0. Cool? All right. So let's move back and let's go to the second example. Okay, so it says determine the points at which the given function has a horizontal tangent. Same thing, right? All right, Alec, what's the derivative?
0, oh wait, 1,
1
plus 2 cosine of x.
plus 2 cosine of x. And because I'm trying to find the horizontal tangent, okay? Nate, what am I going to do since I'm trying to find the horizontal tangents?
You said it equals to 0 again?
Yep, here we go. Set it equal to 0. Okay? So now, Braden, what am I going to do? What do I do to solve this?
Would you subtract 1?
Subtract 1,
Divided by 2.
divide by 2. I like the way you did that. Because I think, guys, you should save a lot of time and precious time with rewriting or writing your answers as far as just go straight to it. Okay? And now we can't forget unit circle. We can't. Yes, Omar?
Why was it equal to 0?
Because a horizontal tangent is when the derivative is 0. I love those questions. Why is it 0? Even if you forget, even just reinforcing, why am I doing this? Don't just do it 0 because you did it in algebra 2. It's for a different reason. Okay? 0 here means something totally different than 0 did in algebra 2. What did 0 mean in algebra 2? Those were x-intercepts. These are what Alex said. Possible horizontal slopes of 0 where the local mins and maxes could occur. Okay? Real quick, just because he went there. Is this a local min and a local max and a local min? Is it?
Yes.
Yeah, it is. But they're cusps. Right? You see that? So, with what we did here, it would only work if it was a smooth curve, right? Whereas this, we would have to do a little bit different to find those points. And it's basically not setting it equal to 0, but setting it equal to undefined.
Whoa, what the
worries. Just real quick, if you didn't get it, no worries. This is how we set, remember, cusps are when the derivative is either, is a vertical tangent or it's undefined. If you're not getting this undefined thing right now, no worries. I was just thinking if I could take either right now. We'll figure that out later. Anyways, let's get back to the problem. Let's find x when I take the cosine of x is negative 1/2. So unit circle time. Here we go. So I'm going to see, look, this is how I would want you to progress it. Cosine is an x value. It's a negative x value, so I'm looking at quadrants 2 and 3. And I want it to be 1/2. So I know it's going to be x-wise, it's going to be 3, 2, 1. So I'm looking at this and this angle. Because this will get me that negative 1/2 that I need as far as an x value with what we learned back in pre-calc.
How do you know that's going to be the... How do you know to do the free ticks and that would be the...
Oh, if you didn't know, if you didn't see this in pre-calc, a fast way that you can recreate the unit circle is doing x's first and then y's. So I could go 3, 2, 1. That's 3 for the x, 2 for the x, 1 for the x. And then going back down with the y's.
Oh, I see.
3, 2, 1. All over 2, square root the top, and put the signs where they go. And with that, you see that this would be a negative 1/2 as a point. At 2 pi over 3. And where else, guys? 4 pi over 3. Because we're looking at between 0 and 2 pi. Questions?
So you're just taking the arc cosine of negative 1/2.
Yep. That's it. And then just bounding it between 0 and 2 pi. Did y'all hear what he said? It's the same as the arc cosine of negative 1/2 is x. Or you could write it like this. Some of you actually write it arc cosine of negative 1/2. Okay? And that looks like that. Arjun, you good?
Yeah, I was trying to figure out what to do.
Okay, okay. So if you need help on that, maybe I might do a quick video when I do that proof of showing why the cosine was positive or negative to become a negative sign and why sine becomes a positive. I'll put unit circle review on that video too. All right. Here we go. Our last example. It's going to be right here. Okay. We have find k so that the function will be tangent to this line. Do you see what's going on? All right. In your words, tell me what we're trying to do. Right? And what are we trying to do?
So, is that the derivative, right?
Okay, so he's asking, is this the derivative? Okay, think about that. Think about his question.
No.
And I totally misspelled that.
Derivative is...
Well, because that's the actual equation.
Derivative?
The derivative would be solving for the slope.
Okay, so hold on, I was laughing. So is this function the derivative is what Braden asked. We let it marinate for a little bit. Christian's adding what to it?
I said no because that actually has an actual slope and intercept, and the derivative is trying to solve for the slope.
And what do you think this slope is showing?
The derivative of a certain point, I guess.
Okay, so you're saying
So, are we looking for...
that his is not correct, that this is the derivative. You're saying no, it has a slope. So what is the slope? 2. Okay? We're putting all these, I want you to hear what other, this is the strategy as far as just building more and more from what other people are saying to get your more in-depth answer just with one example instead of hundreds of problems. Okay? Who else has a theory or an idea? Alec?
Trying to find a value of k.
Okay.
Where the function f of x has one point that it shares with the line y equals 2x minus 9.
Okay, okay. You see how it's becoming, he's putting together everything that's been said, and he's even building even more possibly than what he might have originally thought. And right now he's the closest to what it is. So k could be a value that creates some function, right? In this case it's going to be a quadratic, so it's only going to have like this. Or it could have something like this. Go with me? So we're trying to find what k value would create either something that looks like this or this that will be tangent to this line. So tangent means if I graphed -9 with the slope of 2, that didn't work. -9 with the slope of 2, that one could work. You with me? And it all will happen whatever that at value is, which is what letter?
C.
Someone said it back there. X, right? And k would tell us where this graph would be, where it would be shifted, up, down, wherever. You with me? This is as difficult as today's problems get, okay? This one's a big problem. This is not an easy problem. But I will not tell you that before we start it, because then you'll be like this all to begin with. So this is how we do this. We're going to take the derivative. Guys, if in doubt, take the derivative. That's your rule for that's your rule. That's your rule for the entire first semester. If in doubt, take the derivative. All right, so here's the derivative. F prime of x is equal to what? 2x plus k. K is a constant. Okay? And whatever this derivative is equal to, we're going to set it equal to 2. You with me? Because this is the tangent line where it will have a slope on that entire line of 2. So we're trying to set this function equal to 2 so we can find out where does this occur. Go with me? Okay, so here's one equation that we're going to use for sure. But the problem here is that we have how many variables? 2. Help me out. What could we do? Come on, guys. I want you critically thinking. I'd rather you really think really hard on one problem than, again, 20 example problems that you will lose the point. Pun intended.
Make x equal something plug it into that.
So guess and check. We can't guess and check per se because that would take forever.
Is it possible to substitute x for something?
Close. There is a substitution that goes on for sure.
You solve for k and then substitute whatever it is for. So like.
Check this out. Ready?
K 2 minus 2x, and then do 2x minus.
Here we go.
plus
Ready?
2x.
You're there. You're there. You're there. Check it out. This equation is where the slopes are equal. Do you agree? The slope of the function and the slope of the line. Over here on this other equation, I'm going to show where the locations are equal. So this is where the f of x's are going to be equal. This is where the f prime of x's are equal. So I'm going to take y, aka f of x, and I'm going to plug it right here. You with me? Here we go. So 2x minus 9 is y, otherwise f of x. And it's equal to x squared plus kx. Christian already said it. I still have two variables. But if I use this and I solve for k, I now can write k in terms of x. Y'all with me, guys? So I would have the following. Let's finish it off. I would have 2x minus 9 is equal to x squared plus 2 minus 2x all times x. Because again, I substituted what k was from the derivative function. Can someone tell me why I can do that? What have we talked about today that allows me to do that?
It's like the constant multiple.
Not the constant multiple. Good try, though. Good try. It wasn't the constant multiple rule. Matthew, what has been said today? No? It was because of a two-letter word. At. Because at that x location, the slopes are the same and the locational y values are the same. Okay? So now if I were to solve this, I have, here we go, x squared plus 2x minus 2x squared. And do you see how the x squareds right now, there's a negative x squared on the right side? I'd probably move it over to the left just to make it positive. Okay? And then now, what would I have?
2x's cancel.
The 2 x's cancel, so that you have x is what? 3 and negative 3. So 3 and negative 3 are what these x's could be.
So you plug those back in.
So we plug these back into this equation. And if I plugged into 3, what would k be?
Plus minus. Wait,
No, not like that.
so what? Negative 4.
So negative 4. Now let's plug in a negative 3. 8. So you see it?
Yeah.
Okay, so yeah, you gotta solve it out, but your case could be a negative 8, or sorry, a negative 4 or an 8. And it would make all that criteria still happen.
So if it's a quadratic function where you're solving for k, does that automatically mean there will be two k values that'll make it work? Or does it just happen to be like that?
The way, did you see what he asked? Did y'all hear what he asked? Because it's x squared, will there be two k's per se? Here's what I'll say. Yes, but if I'm talking about time or things like that don't make sense to have negative 3 speed or 3 seconds, or you know what I mean, then you have to real world wise eliminate extraneous solutions.
But if it's just like numbers for this, then it...
Yep.
Okay.
Questions? Your brain should hurt. Your brain should hurt a little bit because there's a lot of conceptual stuff that just happened. And I'm not even kidding. I can't even tell you enough. The reason why your brain hurts is because of a two-letter word, at. Truly understanding what at means and the location of what you're trying to describe. Okay? So, our last problem that we're going to do, our very last one, is this one right here. Now we're going to do this together, okay? And I'm going to teach you some calculator stuff too. Okay, here we go. So at time is equal to 0, a diver jumps from a diving board that is 32 feet above the water with an initial velocity of 16 feet per second. So the diving board, right? Let's make our staircase or whatever. It is 32 feet high. And this person, wherever they're at, right here at the very top, is going to jump with an initial velocity of 16. Is that upward or downward? It's upward, because if it was downward, it'd be a negative 16. So they're jumping up. Duh, divers jump up as they're diving, and then it will end up doing something like that and going into the water. Okay, so here's your diving board way over here. Okay, questions so far? Oh, that's pretty close. Okay, that was cool, wasn't it? Anyway, so I was like, am I the only one? Anyway, so the equation is S of t is equal to negative 16t squared plus 16t, because that's my initial velocity, and then plus 32. Please make sure you identify the t's between addition. Okay, here we go. Arjun, when does the diver hit the water? What do I do? Okay. Let me ask you this. Is this asking for a velocity of some kind? No, so we won't work with the derivative. Not on this one yet. So when does it hit it? Jordy, what would I do? Okay, so she just said another two-letter word that we got to be careful of how we use that. We got to be more exact. It's okay.
Like the negative 16.
There you go. So we have to set the position function equal to 0. Because when you say it, what is it? Is it the position? Is it the derivative? Is it the second derivative? So yes, Jordy's right. We're going to set all of this equal to 0 so that we can see when is the height, aka the position, of S of t 0. And this is where the extraneous solution comes into play, because this would go even more, and there would be a negative time that it could be 0, but that diver's not falling backwards. Okay? I hope not. Okay, so setting this equal to 0, that t will tell us. We just have to pick the extraneous one. Okay? Now, let's find, we're going to do that with the calculator here in just a bit. Find the instantaneous velocity when t is 1. Arjun, what do I do? Find the derivative. So s prime of t, which you could also write as v of t. Notice that I don't have that prime on v of t. Because if I did, I would be talking about what? Acceleration. So I have v of t, aka s prime of t, is going to be equal to anyone. What? Negative 32t plus 16. Okay? And then I plug in my at value. I don't set it equal to 0. Don't get into a routine of just, okay, you do this next, because it's all different. You got to treat it conceptually like a physics-based problem. Okay? So, we're going to plug in 1. That means you're looking for s prime of 1, aka v of 1. Right? So that would be negative 32 times 1 plus this. What does that equal, guys? Negative 16. So at 1 second, this person is traveling downward toward the Earth, the surface of the Earth, at negative what?
16
feet per second. How's that? Okay, and I'll show you with the calculator in just a bit. And finally, the average velocity. The algebra 1 of stuff. Okay? That means find the y value at 2. In other words, what is this as s of 2? That means you're going to plug in 2 right here, whoops, right here, and see what you get. You with me? And then you would plug in 1, because that's your lower a value, or x value, and it would be minus s of 1, all over 2 minus 1. Questions? Okay, so follow me, here we go. What we're going to do is, let me take a picture of this real quick with my phone so that I can type it into the calculator. And then follow me, here we go. So, we'll go back to, let me add a calculator page. I'm going to show you some stuff. First of all, I think you should always store your function. So let's store your function as negative 16t squared plus 16t plus 32. And I'm going to store this, control variable. I'm going to store it as s of t. And you could make this alt f of x if you wanted to. I'm just showing you that you could do it with different variables. Questions? Okay, here we go. The first question asked, when does this equal 0, right? Here we go. Menu, algebra, solve. And you can put, when does s of t, close the parentheses, equal 0? And then just do comma t. It's at negative 1 and 2. So it will hit the water, like we were showing, at negative 1 and 2. And remember, at 1, it was showing the slope of this was negative 16. We get that? The slope of this, it was already on its way down. Okay? And then finally, if I wanted to find the derivative, here we go. Big time shortcuts. And those of you who learn them will finish. Those of you who don't won't finish. Tests that we will have throughout the year that are designed where you're not supposed to finish. So this last test that we had, and I'm just now realizing I didn't mention this at the beginning of class, this was a test that you shouldn't have finished. It was a little bit long. Okay? This one was on accident. But there would be 2 throughout the year that you won't know before the test. But you'll know afterwards if it was one that you weren't supposed to finish or not. And this is the reason why we do this. Because people at your caliber, even when I was your age, it's so frustrating to let go of a problem and move on. So we're trying to teach you, you have to let go and then come back to it later. Okay? But there will be 10 points that will be added to yours because of time. Not because of content, but because of time that will be added to your grade. This is not a curve. We don't give curves. We never will, because curves are given after we grade your papers and we're like, oh, maybe we sucked on it. No, that's not what we're doing. We're deciding this before we even grade papers. Okay? Because we can tell by, like if you notice when you're testing, I'm testing with you. I'm watching your work, and I'm writing out the key, and I'm like, ooh, this might have been a little bit too long. Okay? Alright, so here we go. We're going to find the derivative at 1. Menu, calculus. You're going to press this a lot. Menu 4. 2, derivative at a point. Guys, what's my variable? T. What's my time? 1. 1, right? For that part B. So now this will tell me what's the derivative at 1. All I have to do is just put the function, which is s of t. And there it is. Negative 16 feet per second. And then the last one was, what was the average rate of change? You ready? Here we go. Control divide. S of 2 minus S of 1. Yes, we want to make sure we develop the calculator. And you'll get the average velocity was a negative 32 feet per second. Questions? Outstanding job today, guys. Nice.